Momentum and impulse. A collision is a short duration interaction between two objects. It takes time to compress the object, and it takes time for the object to re-expand. The duration of a collision depends on the materials. So some materials are really squishy and easy to compress and expand, and some of them aren't. You can see that this soccer ball in its interactions is pretty easy to squish. We're going to learn in this unit that there are three different types of collisions. There's collisions where two objects bounce off each other, such as this soccer ball. Collisions where objects stick together, and then collisions where two objects explode apart. Every collision involves impulse. Impulse is a large force exerted over a short interval of time. Here's a graph of an impulse. You can see that this axis is force and this axis is time. If you have a harder force, which is a larger peak, a maximum value here, or if you have a longer duration, which is a wider curve, you can create a larger change in velocity. This makes sense because if you're kicking a soccer ball, like in this example here, if you kick the soccer ball with a large force, that soccer ball is going to rocket away. Versus if you kick it with a small force, then you'll have a small velocity. Or if you kick it longer, like for example, if you like tap it versus you send it, if you have a greater amount of time, that will create a larger change in velocity. And if you kick it for a smaller amount of time, that'll create a smaller change in velocity. So we're going to learn today how both force and time have a relationship with your change in velocity. The equation for impulse is J equals Ft, with J equaling impulse, F equaling force, and T equaling time. It makes sense that the unit is in Newton seconds because force is measured in newtons and time is measured in seconds. We can also say that impulse is a vector with magnitude and direction, which makes sense because force is a vector. So that means that we can have a positive and a negative impulse. Impulse is the area under a force-time graph, which those of you taking calculus might recognize as an integral. Those of you not taking calculus can know that if you have a graph with force and time, that your area under the curve would be impulse. And it's kind of hard to calculate this area without calculus. So you have to approximate this as either a triangle or a rectangle. And then take the area of that triangle or rectangle. You can see for this rectangle right here that there is the approximated area of a rectangle with this side being force and this side being time. And you can see that this empty white space up here is actually, like if you took like this part of the rectangle and flipped it upside down, that space fits in here, and that this space fits in here, as long as it's a like evenly distributed curve. So taking the area as a rectangle is a viable option for some impulses. Momentum is inertia in motion. Here is the equation for momentum. P equals mv. The letter P in this case represents momentum. Its units are the kilogram meter per second, which makes sense because mass is measured in kilograms and velocity is measured in meters per second. Momentum is a vector. So if you were going to draw momentum, you might do so by having a mass with a velocity vector because momentum is mass times velocity. An object with momentum is hard to stop, which is why sometimes in lay people's terms, we will use the idea of a political movement having momentum, or like a person who's like on a roll giving a speech might have momentum, because momentum is hard to stop. Here are some examples of typical momentums. You can see that a car on the highway is probably way harder to stop than a falling raindrop. That doesn't mean a raindrop can't hurt. Like, you can have a raindrop that hurts. That has more to do with pressure than momentum. You have to imagine that momentum being how hard it is to stop this thing. The impulse-momentum theorem connects together the ideas of impulse and momentum, and it comes from the equation F equals ma, which is Newton's second law. So what someone with a big brain did is they said, all right, acceleration is a change in velocity over a change in time. So if you fill that in for acceleration, then you get this right here. And if you multiply time to both sides, then you get force times time equals mass times change in velocity, which just happens to equal impulse and change in momentum. It's change in momentum and not just momentum, because it's a change in velocity. So as this velocity changes, its momentum changes too. You can also have a change in momentum if your mass changes, but that's far less common. As a summary, an impulse, or a force times time, delivered to an object can cause its momentum to change. Just like we saw at the very beginning, if you apply a force to a kickball over a period of time, then that can cause it to move, so changing its momentum. In the same way, if you deliver an impulse to a golf ball, the golf ball's momentum can change and it'll fly away. Or if a soccer player has a ball moving towards its head with a certain amount of momentum, as it collides, you can see right here that there is a force being applied over a period of time, and that can cause the momentum of the soccer ball to change. You can do this by applying a large force for a short time or a small force for a long time. This leads us to the idea of why a baseball hurts if you catch it with your hands, but hurts less if you grab it and pull it back with you. So for the same baseball, the same mass moving at the same velocity, meaning therefore the same momentum. That means that if your collision happens in a smaller amount of time, that you'll have a larger force. And if you can increase the time, that you'll experience a smaller amount of force. You can use the same idea when you ask for the same force. Why is the speed of a cannonball greater when shot from a cannon with a longer barrel? That's because for the cannonball's gunpowder explosion, right here, that's applying a certain amount of force, that if you can increase the time that force is applied, that for the cannonball with a certain mass, you can increase its velocity. So for force times time equals mass times velocity, if your force is constant and your mass is constant, increase in the time will lead you to have an increased change in velocity. This is also why in driver's ed, why do they teach you to hit a deer rather than swerve around it? And that's the same idea if you consider that your two choices are typically deer or tree / other car. You want to hit the deer, obviously, because the deer is softer. So for the same collision, a soft collision versus a hard collision, such as a wall or a tree, if you can increase the time of the collision, you will decrease the force, and vice versa. That does not, however, necessarily change the impulse. So this question says, when a dish falls, will the impulse be less if it lands on carpet versus if it lands on concrete? So for both of these examples, you have the same dish with the same mass, and it's falling with the same velocity. And we want to compare the carpet versus the concrete. So it wants to know, will the impulse be less? Well, there's certainly a difference in force and time, but not necessarily a difference in impulse. So for the carpet, if you have a larger time, you'll have a smaller force, and vice versa for the concrete. But that doesn't change your impulse. Remember that impulse equals a change in momentum, and your momentum isn't changing in either of these examples. which means that your impulse is going to be the same. So you're not changing the impulse or the momentum. You're simply changing the ratio of force to time. In terms of the ratio of force to time, it says if a boxer is able to increase the impact by 5 by riding with the punch, how much force will the impact be reduced? Well, if your time is 5 times as much, that means your force will be 1/5. So the answer is 1/5 and the same. The impulse an object experiences is greater when that object bounces. The impulse required to bounce is greater than the impulse to stop. That's because in stopping, the velocity goes to 0, and in bouncing, the velocity goes to 0 and then to a negative value, meaning it's a larger change in velocity. So like, for example, if this guy drops a ball over here at a rate of 4, and it lands right here at this spot, it has a velocity of 0, and then bounces back to 6. In stopping, its velocity would go from 4 to 0, and its change in velocity would be 4. But if it was bouncing, it would go, for example, from 4 to 0, and then backwards from 0 to positive 6. And its change in velocity would be 10. So there's a larger change in velocity if it bounces. And if you have a larger change in velocity, that means you have a greater momentum, and therefore a greater impulse. That's why it hurts more to be hit by an ice ball than a snowball, because the ice ball bounces off, whereas the snowball stops. This is also why cars have crumple zones. So if a car bounced off of another car, it would cause a large force to the person inside. So cars are specifically designed to have crumple zones to crush, to decrease the chance of bouncing, meaning a reduced force of your collision. It's more likely to total your car, but it's a safer crash for you. Let's calculate the impulse acting on the ball. Remembering the impulse is going to be the area under the curve, and that this curve is a triangle, 1/2 base times height. So to find the impulse, we'll do 1/2 the base, 8 milliseconds, which is 0.008 seconds, times the height of 300 newtons, which would give us an impulse of 1.2 newton seconds. If we wanted to find the average force on the ball, we would take the two forces, add them together, and divide by 2 to get the average, which would be an average of 150 newtons. A girl on skis has a mass of 60, reaches the bottom of a hill moving at a velocity of 20. What would be her momentum? Momentum is mass times velocity. So you'd multiply together 60 by velocity, and you get a momentum of 1,200 kilogram meters per second. If you encounter deeper snow, so here she is, her mass is 60, her velocity is 20, that's her original velocity. She comes to a stop, so her final velocity is 0 in a time of 3 seconds. What amount of force does the deeper snow exert? Using the impulse momentum theorem, I can say force times time equals mass times change in velocity. Force times 3 would equal my mass times my change in velocity, final minus initial, which would give us a force of negative 400 newtons. Makes sense that it's negative because the object is slowing down. A force of 800 newtons is causing an 80 kilogram fullback to change his velocity by a value of 10. What is the impulse experienced by the fullback? This is kind of a tricky question, because if you try and fill in impulse equals force times time, that doesn't really give you anything. But if you fill in impulse equals delta P, that doesn't really give you anything either. So you have to go the next step and say, all right, delta P has to equal mass times change in velocity. So using this equation, you can say that the impulse would be the mass, 80, multiplied by the change in velocity, 10, to give you an impulse of 800 Newton seconds. This next one is also kind of tricky. You have a mass of 0.8, soccer ball experiencing an impulse of 25. What is the change in momentum of the soccer ball? Well, since impulse equals change in momentum, that means the change in momentum would be equal to 25. In summary, any moving objects have momentum. The force acting on an object will deliver an impulse to change that object's momentum. Momentum equals mass times velocity. Impulse is force times time, which is the area under the curve. And this relationship can be written as impulse equals change in momentum. Good work, guys. See you next time.